The video you're about to watch covers the technology of synchronous Ethernet. There's going to be a second video, a companion video to this, which will cover the ITU-T G.8261 and 8262 standards testing for SyncE jitter and wander performance. Okay, this is good. This is very good. Weighted fair queuing. Hello everybody. Just a quick reminder that Cisco CPOC has a YouTube channel, and if you do Googling for Cisco CPOC and look up videos, you soon find the Cisco CPOC homepage, and this shows various short videos on various technologies. As we've had people come through the lab, if we think it's going to be interesting or new, we then make a small video and put them out onto YouTube. So they're there to be looked at and enjoyed, and the video you're about to watch will also be posted on this YouTube tube channel. Subscribe and enjoy. So, carrier pigeon, and they can use the cloud. By way of a refresher, I'd just like to go over the technology involved before we start doing the measurements. There's a couple of things you may want to synchronize in your network. One is frequency and one is time. Frequency is the aspect we're looking at today, and the idea here is you have a router which got its own internal oscillator to clock out these data bits to other routers, and what we do is we have a higher quality oscillator, and this comes into the router, and then the router own oscillator phase locks loops to the external higher quality oscillator, and then these data bits being transmitted out can go to other routers downstream, and of course the other routers downstream can then derive the clock off that incoming data and synchronize themselves to the same high quality clock that's provided here. So this is a slide showing the relationship between data and clock. Typically the clock pulse is derived on the incoming data, so the idea here is that when the clock pulse, as you can see, it's repeating in this particular slide, when the clock is falling down, if you look at the bit period here, this is a logical one. It's actually telling you to sample it right in the middle of that bit period, so you've got more chance there to get a good snapshot or reading of that logical one. And the same here, 0 in the middle of it, 0 there, so on. Here is a circuit which is going to show us some clock and data signals on an oscilloscope. The bottom trace is the clock pulse, and the upper trace is the data. And you can look at it in various ways. This is sort of expanded or zoomed out. In a moment we'll zoom in and you'll get more of an idea of how the clocks relate to the data. And in this particular case, you can see that the rising clock pulse is sampling the data bit in the middle. Just zoom that out a bit more and you'll see it better there. And there you can see the rising clock pulse is sampling a 0 there. So what happens when the clock becomes out of sync with the data? Well, on the left there you can see everything is fine. In this case we're sampling on the falling clock, and we're now getting a snapshot in between each bit period. But this example here is showing where the clock has slipped, and in this scenario the falling clock edge tells the receiver to snapshot the incoming data. And you can appreciate here it could be it should be a 1, but it also could be a 0 because it's in this indeterminate area here. So this is no good at all, and this is why we need to have the clocks synchronized all the time so that we sample the data correctly. Historically, we need clocks to be synchronized from the old days where we had time division multiplexing with the E1s and T1s and the Sonnet SDH air systems of transmission. But nowadays, while it's really for the 2G, 3G and 4G radio access networks that require to be synchronized. And this illustrates what we're trying to do. We have a over here we have the reference clock to the base station here, and the aggregation router is sending synchronous E over to the cell site router, and the timing is the same. I mentioned at the beginning that sometimes you need to synchronize time as well, and this is an example of where the on a cell site router you've got to have plus or minus 3 microseconds between each cell site, otherwise your calls will start to drop off and so on. Some people say, well, why don't we stick a GPS antenna at various locations around the cell sites and stuff, and that could be done, but if you look here on the screen, you can see here this says it all: GPS jammer handheld, and so that could be jammed and mess up your signal. And also, if it's a thundercloud above you, you may not get your signal from the GPS. So it's not recommended to deploy timing systems like this. And this URL will take you to an example there where it says that should not be used as a unique reference in any critical civilian system. So what we have here is a little bit more information. On the right hand side there is an ASR 9K root processor card, and you can see the SyncE0 and SyncE1. So obviously we have backup and active and standby scenario there. And if you think about it, the root processor card has its own standby root processor card, so you've got up to 4 levels of timing there where you can fall back on. Okay, bear in mind that this input, the bits, which is the building integrated timing supply, is where the reference would come in, and it's also possible to configure this from the command line to make it an output. So you could, for example, have bits coming in here and use SyncE1 as an output to synchronize a local device, or it could be a router downstream and you want to take the timing off the router to synchronize another device downstream. So I'll just read this to you. The router's internal oscillator becomes phase lock loop to the external clock source, primary reference clock. Therefore, the data checked out of all the router's ports is disciplined to the PRC, allowing downstream routers to lock their clocks to the incoming data bits. The router's internal oscillator shifts gear from stratum 3 to stratum 2 when the external clock is selected, and of course providing the quality of that clock is at stratum 2. In the world of clocks and quality, stratum 1 is the best, stratum 2 is extremely good, stratum 3 is what you normally get out of the box on a router. Just Google stratum and you'll find the different informations for that. So how do we distribute timing across the network? Well, there's 2 types of way of doing it. One is the physical layer, and this is what we'll be focusing on, and it's also known as the synchronous Ethernet. This is a physical layer. There's also another way, which is packet layer. You've probably heard of 1588 version 2 precision time protocol and so on. This is not part of this presentation, but this is another technique to get information, clocking information from the source to the destination. and that is using a stream of packets to do this. But what we're looking at here is the synchronous E way of distributing timing. And this is showing you the old world. This is when the Vikings were flying around or sailing around the North Sea. And this is your synchronous Ethernet clock. And this is, you can see the timing coming in. And it's using these Sonnet or SDH. And it's using synchronous status messages here. This is way back in the 60s and 70s and so on. And then we come into the newer world where we are now, where we have the EEC, which is the Ethernet equipment clock, and part of that, the sort of equivalent, and where we had the synchronous status message, and now we have this ESMC, the Ethernet synchronous messaging channel. And this is a fairly basic way of communicating between two routers, saying that say for this router here, for example, he's looking up to this guy, and the Ethernet synchronous messaging channel, he's sending not only the timing, but he's also sending a message saying primary reference clock, and he sees that and says, okay, you're telling me you've got a good clock, I'll synchronize to you. Okay, the lab itself consisted of a ASR 9912 Tomahawk line card and root processor and switch fabric. This was the latest version of the ASR 99 family of line cards and root processors. Tomahawk is an internal name for it, so to measure it, we have a GPS to a time provider 5000, and he extracts the timing information off the GPS signal and outputs, in this case, a 2 MHz clock. One of the outputs goes to the tester. This is the Calnex Paragon X tester, and the same output is sent out to the 9912 router, and this router is then told to synchronize to this incoming 2 MHz clock, and then any data being transmitted out here will be referenced to that clock. This is just showing the old world and the new world, I guess. This was the first 2-port 100 gig line card that we had, and it's using these rather large transceivers, and with the new line card we can now squeeze 8 100 gig line card ports into a line card, so we have 8 100 gig ports here. We're using these CPAC optics, which are much smaller form factor than these big guys here. Another feature here, you can plug in a special CPAC here transceiver, and it allows you to, via this special cable, to instead of having one port at 100 gigs, you can have 10 ports at 10 gig. And this is another slide showing the same thing, but let's have a look at the infrastructure between the time provider 5000 and the clock and all that stuff. So this is a photograph above building 11. We're here at Bedfont Lakes, and this is the antenna on the roof, and then it goes through a lightning arrestor, and the cable comes down to this guy, the time provider 5000. And you can see the green GPS light is lit. This is the cable coming in, so the GPS signal comes in. A DC component is sent up the cable, up to this guy, up to the antenna, where there's a low noise amplifier that gets powered from the time provider here. So this guy extracts the timing information and squirts it out either as 1588, you can choose here, or you can choose to go for 2 MHz out here. There's an interface there that gives me 10 MHz as well, but in my case I'm just using 2 MHz here. So this cable, coax cable, goes off and it rounds to the root processor card, and so it comes into this synchronous E socket here, and you see the green light is on, and that means that the router is happy and it's seeing a good external reference. On the Calnex side, the tester has got basically a reference input, which is, remember, the 2 MHz, which goes in at the back, and then we have 2 ports. This is a 10 gigabit port, which can be XFP or SFP plus. I'm using the SFP plus interfaces at 10 megs, or I could go to 1 gigabit down below there if I desired to. Bit of management there to the laptop, and this is the user interface for the Calnex. And what we're doing here is we're basically sending, port 2 is transmitting information into the device under test, and then we're measuring the signal coming back and comparing it. And this is just to show you how we're measuring it. We don't have a 100 gig interface, so what we're using is this special CPAC, which gives us the cable that gives us these separate 10 gigabits per second ports, and we're using these to communicate back to the Calnex on here. So what we're measuring, we know about clocks, you know about data and so on. Well, all we're measuring is the difference between the reference signal and the so this is the reference signal derived, if you remember, from the GPS, and this is the received signal coming back. And what we're doing is, or the Calnex is doing, is taking the reference and comparing it with the phase difference. This is greatly exaggerated here, between the reference and the received. And this has to be within a certain parameter, and you're looking at nanoseconds for it to be passing the various ITU standards. So there are some references or terms you need to understand, and one is tie, and this is calculations based on the phase error measurements. So this is the time interval error. So this is actually the difference between the reference and the measured difference over an observation period. And this is the time interval error measured in nanoseconds. And then the M-tie is the maximum time interval error. So let's say, for example, we measure this over, say, 12 hours, then we will be measuring the all of these data points are put in a database. And so we'll have the time interval error, and then the M-tie will be the maximum over that observation period of, say, 12 hours. And then the time deviation is the RMS value of the M-tie, which gives you more statistical information. The synchronous E has this special signaling channel where the neighbours sort of talk to each other, and it's the Ethernet synchronous messaging channel. Let's just suppose we didn't have that channel, and this is my network element, my router here, and he can see a clock coming in. He's getting his clock from there, and he's getting a clock from there, but he has to decide which particular clock to use. This guy's not too bad because he's only got one choice in this case. So we would have to, and this is my primary reference clock, which is that's the better one, and then the SSU here, A, is if you will the slightly worse clock than the PRC. So ideally I'd configure him to use the PRC, and then if that was to fail, such as a signal failure or a external command, then it would flip over to this guy. But now let's introduce quality level. So we have the same sort of reasons why we would select external command, signal failure, but we now have the quality level. So the quality level is where this guy's now got this Ethernet synchronous messaging channel running between these two, and they're talking to each other, and this is all part of SyncE, and this guy is saying, use me, I've got a primary reference clock, and this guy is saying, okay, I'll use you. This is coming back with a quality level of saying use me, but I'm an SSUA, so I'm not quite as good as the PRC, so he'll select this. And then this guy here, again, he'll see use me, I'm a primary reference clock. in a way, you don't want a clocking loop. So this network element here will send a message back saying do not use, because DNU, do not use, which means if there was a failure here, you don't want him to start clocking off him because he's providing his clock already. Let's look at a scenario. So this is a network, and before everything goes completely wrong, we have a primary reference clock out to this SSU, which is a synchronization supply unit, which is a way of distributing timing across a comms room. And you can see that we've got this sort of ping pong going on here with I'm the primary reference clock and he's saying do not use me, and the same goes to here. So this is my Ethernet equipment clock, this is my ASR 9K for example, and he is now receiving the reference clock and saying to him do not use. Becomes more applicable for this guy than this guy. So here this is an ASR 9K downstream, and he is seeing the primary reference clock coming in, so he's syncing to him. And he's sending back a do not use to prevent clocking loops. The SSU is also synced to the primary reference clock and saying do not use, and blah blah. So let's now break something. So this is the moment something breaks, so we have this red cross here representing the cut of the cable. So right away this guy sees nothing coming in from the primary reference clock and so on. So the SyncE channel is lost. He now sends an output to the SSU saying I'm the Ethernet equipment clock, help me basically. And he's now saying, notice he's saying not do not use, he's saying use me SSUA. And this guy here then picks up the same signal and syncs to the same line and says do not use back. A few moments later things have stabilized, and this ASR 9K is now saying is now synchronized off the SSUA and saying do not use, because this has got its own oscillator in there. On the Calnex side, the tester has got basically a reference input, which is, remember, the 2 MHz, which goes in at the back, and then we have 2 ports. This is a 10 gigabit port, which can be XFP or SFP plus. I'm using the SFP plus interfaces at 10 megs, or I could go to 1 gigabit down below there if I desired to. Bit of management there to the laptop, and this is the user interface for the Paragon X. So here I'm just setting up for some synchronize SyncE testing. Okay, there's the screen itself. On the left hand side you've got all the buttons to configure things, and then the yellowish frames on the right hand side are the actual results and measuring and stuff. I'm just going to go into the 9K now and see what clock the 9K has selected. It should be the sync 0 clock from off there it is, sync 0 on CPU 0. So now I know the 9K is synced to the reference clock. I'm going to compare the clock coming off one of the line cards with the SyncE with the reference clock. The green line shown there is the result of the individual measurements of the phase, and it's rather like an oscilloscope line, if you will. So let me just set this up. So any deviation from the reference, you'll see it on that green line there. But at the moment it's pretty quiet, and the yellow and green quality levels at the top there are rather a bit like a PCAP in one respect, but just for the synchronous messages between both neighbours, the 9K and the Paragon X, which is pretending to be a neighbour to the 9K. So what I'm going to do as a bit of fun here is go into the 9K and pull out the sync cable, its reference, and we'll see what happens. So this is me in the 9K, showing the fact the router is now 9K selected, the sync 0, and you can see the QL level is PRC, primary reference clock, and the priority is 1. 255 is the lowest, and there I'm writing on the command line. So I'm going to go and pull the sync cable. So when I pull the sync cable, the only available oscillator left for the 9K is its internal oscillator, and you'll see on the right hand side of the screen where the green line is some disturbance. So there's a syslog coming in saying that we've lost the sync 0 clock and failed over to the internal clock, and there's the effect of that, and there's the phase measurement difference, as you can see there. Obviously the 9K could have been given a secondary clock off another, maybe a 10 gigabit line or a 1 gigabit line, and it could have been failed over to that. But in this particular lab I've just got the internal and the external, and there you can see now on the command line it's saying it's failed over. So as I'm typing there, I'm now going to go back into the lab and reconnect the reference clock into sync 0 on the root processor. The 9K will see that come back, see it's stable, and then revert back to timing itself off that. The green waveform on the right hand side, you'll see that you see it's tracking away at the minute. It's going up to the right. You should see it sort of bounce and come down again. There we go. So now I've just plugged in the clock, reference clock, to the 9K, and there's the message and the log saying it's in holdover mode. There is where the 9K sort of doesn't trust it's come back, and then eventually it decides it has come back and moves over. And now there we can see that the QL level is PRC and it's off that sync 0. So this Calnex X is quite nice because you get to see, there's me zooming in, you get to see what has been happening on the measurement. You also get to see the SyncE messages. There's in the yellow and the green. And you can also combine the graph so that you can see the actual phase measurement and also when the quality level changed. I should be able to just put that, we'll bring up another graph in a moment. These data points being measured are put into a database, and then there's an offline utility. I think it's called CAT. You can just see it on the bottom of the screen there, and that crunches these numbers and puts ITU grids on there for pass and fail for different tests. So there you can see the result of me pulling the cable and then reinserting it. Now let me just get that second screen up. I'm just trying to show you there how it changes the QL levels from primary reference clock to... No, I went too fast there. Let's put the other graph on. Show a second graph on, and then I'll keep the bottom one the same and change the top one to show the QL levels. and you can see there where everything was fine and we were sending or receiving a primary reference clock, and then we went to a do not use or secondary, and then I plugged the cable back in and we went back to primary reference clock. So this is the 9K sort of saying to its neighbour, I have a reference clock, now I've lost it, now the reference clock has come back. In fact, in this case the neighbour's the Calnex X. Very nice. Okay, this concludes this talk on SyncE. My name is Peter O'Reilly, and I hope you've enjoyed it. Bye bye.